Hi everyone. Welcome to the last day of Limit Camp, and today we have Professor Bhattacharya. So, uh, just a few words about him. He did his PhD from Stanford University, and he completed his bachelor's and master's from ISI Kolkata. And now he is a faculty member at University of Pennsylvania. And he has been recipient of various prestigious awards like NSF Career Award and the Sloan Research Fellowship. And his research interests are mainly in the intersections of statistics and probability. And with great honor, I welcome Professor Bhattacharya to deliver his talk.
Thank you, Shanchan. Thank you for the invitation. I'm very happy to be speaking here. I wasn't aware of this camp until very recently, so it is very nice to see that the students are organizing this, and I'm very happy to be speaking here. So today I am talking about statistical centrality measures, facility location, and Voronoi games. This is a topic which is sort of at the intersection of statistics, some geometry, and some algorithms and computer science. And so hopefully there will be a little of something for everybody. There will be lots of problems, lots of open questions, and lots of puzzle-like things. So if anyone is interested, have some free time, you can think about some of the problems. So before I get to the details, let me start by saying give a broad roadmap of the talk and also a personal anecdote, a personal story. So I started working on these problems a long time ago when I was doing my bachelor's at ISI, almost 20 years ago now. And I did continue to think about these problems a little bit after I left ISI, but my PhD and subsequent work were on other things, so I kind of moved away from these kinds of problems. And then, when I started my job at UPenn about 8-9 years ago, one day I got an email from a colleague of mine who I didn't know at that time. His name is Ricardo Castillo Nera from the epidemiology department. And their group at UPenn were working on designing rabies vaccination campaign in Peru in South America. And they wanted some help with some geometric optimization algorithms and some statistical modeling. And they saw that I had some work on that, and so they reached out. And it was while working with them and in understanding the various practical challenges in designing such campaigns, we were able to formulate new theoretical problems. So I started off in theory. By some lucky coincidence, I got involved in some applications, and then it's from working through the applications we were able to find some new theoretical problems. So it's a story about going from theory to practice and back. So I will start by saying a few basic things, some background stuff about statistical centrality measures and facility location. It's something that connects geometry, computational geometry, and statistics. And then I will mention briefly some of our work on Voronoi games and some open problems and questions. And then in the end, I will talk a little bit about the rabies campaign and how these ideas were relevant there. So I can't see the audience here, but I will try at least for the first few slides, maybe to be interactive if possible. So I might ask a few questions. If you have something to say, just go ahead and say it, because I can't really see you guys, but please interrupt me, and if you have any questions, do ask me. So one of the basic and most well-studied and well-known problem in facility location, which leads to a very basic notion of statistical centrality measure, is that of the one median, or the Fermat-Weber problem. So what is this problem? So suppose you have n points in d dimensions. Always think of d as 2, that's easier. Everything can be done in d dimensions, but think of 2 dimensions, that's easier. So these are some points. You can think of them as each one of your houses. And these are the users. And I want to place a new point Q, which is going to be a facility, like a hospital or a petrol pump or something, in such a way that the users, each one of us, don't have to walk too much. So a basic way to do it would be to find a point Q which minimizes the sum of distances from Pi to this point Q. So the Fermat-Weber point Q is the point that minimizes the sum of distances, the sum of Euclidean distances from the point Pi to the point Q. So if you are in one dimensions, if all the points are on a line, then this is just minimizing sum of absolute values, right? So this is nothing but the median. This is the median of the endpoints, right? So in 2 dimensions, this problem was originally proposed by Fermat many years ago for 3 points. So Fermat considered 3 points A, B, C in the plane, and he wanted to find a point Q such that the sum of Q from A, B, C, sum of the distances from Q to A, B, C is minimized. So I'll come back to Fermat's problem in just a moment, but this problem was later reappeared in the facility location in the geometry literature by Alfred Weber, who used this as a measure of placing an optimal facility, an optimal gas station or optimal convenience store or something. And in the statistical context, this problem was studied by Halden again many years ago, and Halden used this point Q as a notion of multivariate median. So if you're in 1 dimensions, it's very clear, we know very well how to define a median. But if you are in dimensions 2 and higher, there is no natural notion of ranking. So defining median for multivariate data is a delicate matter, and Halden suggested using this point Q, which is obtained by minimizing the sum of distances, which coincides with the median in 1 dimensions, as a notion of median in dimensions 2 and higher. So this point Q, the optimal point Q that you get out of this problem, is also often known as the geometric median. Okay? So this is the 1 median problem, or the geometric median problem. Now, as I mentioned, this problem was proposed some 400 years ago by Fermat, and it was solved a few years later by Torricelli. So he had 3 points A, B, C in the plane, and Fermat asked, what is the point Q, which minimizes the sum of distances? So does anyone know the answer, or anyone has a guess of the answer?
Is it the centroid?
It's the centroid. So centroid is like center of mass, right? Something like that. It's like the average point or something, right?
Yes, it's a kind of where the medians intersect.
But the medians intersect. Okay, centroid where the medians intersect. Okay, that is a natural guess. Any other guesses? Well, so you can make a bunch of guesses. It can be centroid, in-center, circumcenter, and stuff like that. But it turns out that the solution of this problem is not one of the standard points that you see in classical geometry. In fact, the solution is the point which subtends angle 120 from each of the sides. So this result was proved by Torricelli, and this point which subtends angle 120 from each of the sides is called the Fermat-Torricelli point. Right? So, okay, so Torricelli proved this, but the solution of this problem is still incomplete. Why is this solution still incomplete? So this is a solution, Torricelli proved that this is the solution, but I claim that this is not the complete solution. This is not solving the problem completely. Why so? In what cases this cannot be a solution?
The point may lie outside the triangle in some cases.
Exactly. So if there is an angle which is bigger than 120, then this point will lie outside the triangle. And there is no way you can find the optimum will be outside the triangle. That is impossible. So this solution that Torricelli gave did not cover that case. And this case was actually open for many, many years. Now, in this case, we of course now know what is the answer. If one of the angle is greater than 120, then the Fermat-Torricelli point is the point which is obtuse, is this point. It coincides with the point whose angle is bigger than 120. In fact, this problem, even though people kind of knew the solution, was never properly proved for many years. And this case was noted in Courant and Robbins' book in 1941, and I think one of the first proper correct proofs was given only recently. So even for 3 points, this problem has an interesting story. It goes back to Torricelli, and there are 2 cases depending on whether or not the point is inside the triangle. If it is not inside, then it is the obtuse point. Right? Now, there are a few other cases where the Fermat-Torricelli point can be explicitly found out. So instead of 3 points, if we have 4 points, then also we know what the solution of the Fermat-Torricelli point is. So there are 2 cases here. If the 4 points form a convex quadrilateral, then the point is the intersection of the diagonals. This is some triangle inequality. You can apply and prove that. In the same case as the triangle, a case was missing for centuries. So Pagano in 1775 proved this when the points are in a convex position. But the solution when the points are in non-convex position apparently was never looked at very carefully. And then it's only recently that Frank plus Tria showed that if the 4 points are not in convex position, then the Fermat-Torricelli point is the point which is non-convex, is the non-convex vertex, right? So for 3 points, we have a full solution, and for 4 points, we also have a full solution. But there are some interesting cases. Now, in general, if you have n number of points, even in 2 dimensions, the Fermat-Weber problem, the Fermat-Torricelli problem, does not have a closed form description. In fact, it turns out that there is a very interesting result by Bajaj from about 30 years ago, which says that if you have 5 points in the plane, then it is impossible to construct the one median or the Fermat-Torricelli point using a ruler and a compass. So not only can you not find a closed form, it is not possible to construct it by ruler and compass. So really, in 2 dimensions and in general, there are only a handful of cases with 4 points and 3 points where there is an explicit solution. In other cases, the solution does not have a closed form, and you cannot find it using ruler and compass. So in general, if you solve this problem, you have to use some iterative algorithms. And the classical algorithm that one uses is by Weisfeld from 37, from the early 30s. And this gives you a way to solve this problem iteratively and come close to a solution. However, the Weisfeld algorithm might not always converge. So more sophisticated versions of these methods are now known. And the best possible algorithm is one by Cohen et al. From like 10 years ago, which gives the epsilon approximation. So it's an algorithm which runs efficiently, and it comes epsilon close to the true solutions in a reasonable number of steps. Okay, so that's the state of the art, really. So that is the one median or the Fermat-Weber problem. Any questions? So the Fermat-Weber problem or the one median is one way to define a notion of center, one way to place a facility. There are different other ways one can possibly try. And one other option is what is called the one center problem. So here again, we have the same setup, a bunch of users in the plane. I want to place a new point Q, where instead of minimizing the sum, I want to minimize the maximum distance. So place a point Q such that the maximum distance from Q to all the points is minimized. Why minimize the sum? It's as reasonable to minimize the maximum, right? So this is another option. This is called the one center problem. So in 2 dimensions, if you think about it, the solution of the point Q, if you place a point Q, place a point at the solution, and you look at the farthest point from Q and draw a circle with that radius, that will contain all the other points. So the point Q is the center of what is called the minimum enclosing circle, the circle which contains all the points, which has the least radius. And it has interesting geometric characterizations. First of all, it can be computed very easily in linear time. is an old algorithm of Megiddo, and it lies on what is called the farthest point Voronoi diagram of the points P1 to Pn. So I'm going to take a moment to introduce what is a Voronoi diagram, if you haven't seen this before, and what is a farthest point Voronoi diagram. So what is a Voronoi diagram? So this is a basic concept in computational geometry. It's very, very simple. So if you are given a bunch of points in the plane, I have 5 points here. A Voronoi diagram is a partition of the plane into 5 regions, which has the following property. If you take any point in this region, then the distance of that point from P4 is smaller than the distance to any other point. So each cell has the property that the point in that cell, the red point in that cell, is closer to that point than to any other points. So it partitions the space into some regions so that each region has the property that if you take a point in that region, it is close to its corresponding point that you have. So if you have 2 points, this is the Voronoi diagram of 5 points. If you have 2 points, P1 and P2, how do you find the Voronoi diagram? What is the Voronoi diagram of 2 points?
It may be the middle of the line segment and where you draw perpendicular.
So it is the perpendicular bisector of the line P1 to P2. One side is the region of P1, the other side is the region of P2, right?
Yes, yes.
And in general, if you have 5 points, you draw all these into 5, like choose 2 10 perpendiculars, and you get these intersection, and that's how you get this region. So that is the Voronoi diagram. Now, what is the farthest point Voronoi diagram? So it is a related concept where you flip the notion of distance. So here, again, you have 5 points, and you want to partition the region into some regions, not 5, but some regions. So each point P1, let's say P1 has a region, this is the region of P1, and it has the property that all points here are farthest from P1 than any other point. So it's a partition of the region, partition of the plane into regions. Each region has the property that it is farthest to some point than any other point. So this set of points is farthest to P1, this set of point is farthest to P2, this is to P3, and this is to P4. Note that P5 has no region, because P5 is at the center and no point is farthest to P5. So the region of P5 is actually empty. So that's the farthest point Voronoi diagram. So again, another question is that, suppose I have 2 points P1 and P2. What is the farthest point Voronoi diagram of P1 and P2? You just told me what is the Voronoi diagram of 2 points in the perpendicular bisector. What is the farthest point Voronoi diagram of 2 points P1 and P2? So I need to partition the plane into 2 regions such that all points in one region will be farthest from some point and all points in the other region will be farthest from some point. How do I do it?
Is it the line passing through one of the points?
So if you take a line passing to one of the points, then how do you take that line? So think of the Voronoi diagram. The Voronoi diagram is P1, P2 perpendicular bisector. All points on this side is close to P1, all point on this side is close to P2. What is the farthest point Voronoi diagram?
It's the same.
It is the same, but the regions are flipped. It's the same line, but the region corresponding to P1 is on the P2 side, and the region corresponding to P2 is on the P1 side, right?
Okay.
Right? So that's how you do it. Like that's how you compute the Voronoi diagram and the farthest point Voronoi diagram. You do it for every pair. You draw these lines and you see what region it forms, and you get the diagram. Now, a property of the farthest point Voronoi diagram is if you take any point on the farthest point Voronoi diagram and you find the point which is farthest from it, that circle will include all the points because it's farthest. Everything is inside that thing. So the minimum enclosing circle center is somewhere on this Voronoi diagram. That's what I told in the last slide. So that is sort of where the center of the minimum enclosing circle can possibly lie. Okay, so it has some interesting geometric connection. Okay, so far I introduced the one median problem and the one center problem, right? Now, as you can imagine, because the name suggests that instead of this is about placing one facility, one hospital, or one convenience store, we can place not one but k of them. So this gives me the k median or the k center problem, and it's defined in a very similar manner. I have a bunch of points in the plane. I want to place k facilities q1 to qk. In the k median problem, what I will do is I will compute the distance of each user to the closest facility. Now I have many choices, so I go to the closest one. I compute the distance from each user to the closest facility, and I sum it. That gives me the k median problem. If I take the distance from every user to the closest facility and look at the maximum, and then minimize it, it gives me the k center problem. So same as before, instead of placing one facility, I want to place k facilities. So these two are standard classical problems in algorithms. They are both computationally difficult if k grows as part of the input. So there's a long line of algorithmic work in trying to find efficient ways to approximate these problems. These efficient approximation algorithms are sophisticated and at times may be hard to implement. So in practice, often people do some heuristic search algorithms to find these solutions. So if you want to do a facility location problem, two of the standard things that you can possibly do is either the k median or the k center. Okay? All right. Any questions? Okay, so that's some basic introduction. So let me now talk a little bit about Voronoi games and some results that we obtained a few years ago. So Voronoi games are facility location problems which are played in a competitive scenario where you have some users in the planes, each one of our houses, and there are two competing companies. Two companies who are giving the same service. They want to place some facilities in the area, and they are competing with each other. So maybe player one will place a facility, player two will place a facility, one after the other, and each wants to optimize the number of people it serves. So that is the game theoretic version of these facility location problems. So here is a setup. I have endpoints in a playing area somewhere. The playing area will usually be a line or a rectangle, just to be simple. There will be two players, P1 and P2 will be two players. And each player will place one facility for R rounds. So the game will go for R rounds. In round one, player one will place somewhere, then player two will come and place something. In second round, player one will place something, and then player two will place something. And this will go on for R rounds. Then what is my goal? The goal of each of the players individually is to maximize the number of users that it serves. And what do I mean by that? I'm always assuming that users are going to the closest facility. So in the end of the game, I look at how many users are in player one's court, how many users are in player two's under player two's area. Whoever has more wins the game. Okay? So that's payoff. So the player with the larger payoff wins the game. So this will be referred to as the R-round discrete Voronoi game. Okay. Now, this work appeared first in the literature of economic statistics, work of Hoteling and Stackelberg, and then more recently in computational geometry. And there has been many variations started in the last several years. So what we will do here is study the basic case where endpoints are on a line. Even in this case, when the users are on a line, we will see in a moment many questions remain unanswered. Okay? So is the setup of the problem clear? I have a bunch of points on a line, U1 to UN. These are my users. all of our houses, imagine they're on a line. They are not, but imagine they're on a line. There will be 2 players. They will play the game for our rounds. Player 1 will go, then player 2 will go. Player 1 will go, player 2 will go. Do it for our rounds. Then we will measure which of the users are closer to which of the players, count whichever is bigger, that person is the winner. Okay? So here is a very simple problem. I have n points on a line, and I want to play the game for 1 round, which is a very trivial matter. Player 1 will place 1 user, player 1 will place 1 facility, player 2 will place 1 facility, right? So this is very easy. I have my points on a line. Player 1 will place F1, player 2 will place S1. So what does player 2 do? Well, player 2 will only make their move after player 1 has placed something. Player 2 can see what player 1 has done. So if player 1 places, these black points are my users, player 1, let's say, placed somewhere, then what is the optimal way for player 2 to do it? Well, player 2 will see on which side of F1 there are more users. There are 3 on this side and there are like 5 on this side. So of course, player 2 will place on the side where there are more. So the strategy of player 1 is absolutely trivial. The strategy of player 2 is absolutely trivial. Just look at where player 1 placed and then just place it on one of the sides which has bigger number of users, right? So the question is, what does player 1 do? What is the best strategy of player 1? What do you think? So player 1 now has to make sure that they do not lose most of their users to player 2. So player 1 has to protect themselves from player 2's best move. So what is the best strategy for player 1?
Maybe they place their facility where the equal number of users on the both sides.
Absolutely. It must place it where they're equal on both sides, because if one of the side is more, then the more side is gone to player 2. So player 1 will place it at a point where there are equal number of points on both sides. That point is the median, right? So player 1 will place it at the median of U1 to UN, right? So F1 is the median of the set of users. If you place at the median, then both sides is half. So at least they can ensure to get half. Okay. So one thing to note here, it's a trivial matter, but I will come back to it in a moment, is that in this example, we note that player 2 always get at least half fraction of the users, half plus minus 1, but anyway, asymptotically at least half fraction of the users. Wherever player 1 places, even if player 1 places the best way at the median, player 2 will always get at least half. If player 1 places at a place which is not optimal, you will get more than half. But always, irrespective of wherever player 1 places, and irrespective of how the black points, the users are arranged, player 2 can always get half fraction of the users. So player 2 can always tie the game. Many times it might win the game, but it can never lose. I mean, if it plays optimally, it will never lose. So it will always tie the game, right? So this is a very simple case. You play the game for 1 round. Nothing is going on here. It's very easy. So what if we play the game for 2 rounds? So now the situation is more complicated. Player 1 will place F1, facility F1. Player 2 will place S1. Player 1 will then place F2, and then player 2 will place S2. Okay? So what do I do? So in this case, finding out an optimal strategy is more complicated. So what we want to do is we want to find the worst case payoff. We want to say that what is the minimum that every player can ensure? What is the minimum that every player can ensure, irrespective of how the other player plays and irrespective of how the points are arranged, right? So here is a definition. Definition is not important. I just told you what it is. So eta 2, given a set of users, I denote by eta 2, the maximum possible payoff that P2 can get against any strategy of P1 when the game is played for 2 rounds. So you're given a set of users. I want to know what is the best that P2 can do. given that P1 is playing in the best possible way, or whatever way, okay? And then I define eta 2 as the worst case payoff over all choices of the users. So eta 2 is essentially the minimum value that the second player can get for all possible strategies of the first player and all possible user configurations. And you define eta 1 in a similar manner. So let's start by looking at eta 1. Eta 1 is the minimum that a first player can ensure. What is a trivial bound on eta 1? So the game is played for 2 rounds. What is the minimum number of users the first player can get? A trivial bound that comes to your mind. So F1, S1, F2, S2. Game is played, you look how many are served by the first player. Whatever be the value of S1 or whatever be the arrangement of users, the first player can always get a certain amount. What is a trivial bound on that? Absolutely trivial bound on that. What is a trivial way a first player can play? Not very clever, just like the something. So the users are there, U1 to UN, right? First player has to place 2 facilities. What can the first player do to ensure that it gets something?
Again, at where the equal number of users both side?
No, so the first player has to place 2, not 1. He has to place F1 and F2. So you have to tell me where is the location of F1, where is the location of F2. So in the previous case, we placed it at such that it's n over 2 and n over 2, right? So now I have to place F1 and F2. So what is a very natural way to place F1 and F2?
1 by 3 and 2 by 3.
1 by 3, 1 by 3, 1 by 3, right? So clearly, if I place my users F1 and F2 such that there are n by 3 points in the first interval, n by 3 between F1 and F2, and n by 3 on the right of F2, then the second player will place 2 facilities, and one of these intervals must be empty. Because there are 3 intervals, and one of them must be empty. And that entire interval, all the users will be the first players. So n over 3 is a trivial bound. It's like a really stupid strategy on the first player's part, but this is a strategy that ensures that the first player gets at least n by 3. Now, although this strategy is absolutely trivial, it turns out that there is a configuration of users. So most of the time, this strategy is going to be bad. However, there is a configuration of users for which this strategy is this bound is essentially tight. This is a surprising fact that there is actually an arrangement of users you can construct such that for that user, however clever the first player is, they cannot get more than n by 3. Impossible. So in a sense, what it means is that eta 1 over n, in the limit, the worst case payoff is actually 1/3. So this trivial bound that you get by doing this nothing observation is actually tight. Okay? Which is an interesting fact. So that is the first player's worst case payoff. What is the second player's worst case payoff? So let's look at that. So what about eta 2? So here, it's more interesting. So what does eta 2 do? So this is the strategy of the second player. So I have to give a strategy of the second player. So here is the strategy. So what would the second player do? So the first player, let's say, placed at F1. And F1, let's say, has the property that it has k points to the left of it, and n minus k points to the right of it. So k points to the left of it, and n minus k points to the right of it. Then the first move of the second player is the following. The second player will take the following move. The second player will place S1 such that there are k points here. So if F1 has k points to its left, S1 will place n by 2 points away so that there are k points to its right. Does that make sense? So this is F1. my first move is S1, so that there are n over 2 points here. Okay? This is my first move in second player's first move. Then what happens in round 2? Well, now second player's move will depend on the first player's move. So there are 3 possibilities. The first player can place a facility here, or here, or here in these three intervals. And we will see, I will do the calculation, it's very easy. In all of these 3 cases, the second player can always get at least n over 2. And this is very easy. So case 1 is that second player places on the left interval. First player places F2 in the left interval. Then second player will just place S2 right next to F1. So this entire middle interval is second player's. So second player gets at least n by 2 in this case. In fact, much more than n by 2. This entire right side is hit there. So it's n minus k. The second case is if F2 is in the middle interval. Then second player will place to the left of F1. Then how many does the second player get? K from here and n minus k from on the right side. So total of n by 2. N by 2 floor, n by 2 ceiling, same thing. Okay? And then the last case is if F2 is on the right interval. And then again, what the second player will do, the second player will place right next to F1. And then get this entire interval. Right? So in all the 3 cases, what we saw is that in the 2-round game, the second player has a strategy that allows them to get at least n over 2. Right? So in other words, the second player can always tie the game even in 2 rounds. So in 1 round, trivially, the second player could tie the game. But in 2 rounds, also, the second player can always tie the game. The second player will never lose. The first player can lose. The first player can get n over 3. But the second player will never lose. Okay? Any questions? Okay. So this is 2 rounds. So what about R rounds, right? This 1 round is done, 1 round is easy, 2 round is also not that hard, 2 round is done. What about R rounds? So using the same logic of placing facilities in equal intervals, if you think about the first player, you generalize the same argument and place R points so that there are R plus n over R plus 1 points on each of the segments. You can show that the worst case payoff of the first player is 1 over R plus 1. That the trivial strategy that the first player can get is in fact attained in the worst case. So for the first player, it can be very bad, 1 over R plus 1. But what about the second player? How much can the second player do? The second player in the previous 2 cases always got n over 2. What about general R rounds? So here the situation is much more delicate. And so in a result we obtained a few years ago, we have the following bound, which says that for any R greater than or equal to 3, eta 2 over n is this number, some number. This number is of the order 1 over square root of R. It's a constant. If you forget the constants 8 and 2, it is essentially of the order 1 over square root R. So what it means is that the second player has a strategy that guarantees n over square root of R. So it can always get a constant fraction, but it is far from the n over 2 thing that we got in the previous 2 cases. Is this bound tight? We don't think so. So we conjecture that in fact for the R round game also, for any R, the second player will likely tie the game. So this is a result. We don't know the answer to this question. If anyone is interested, if you have some time, this is a puzzle. You can think about it for R equal to 3. So is it true that for R equal to 3, there is a strategy such the second player ties the game? Or you can find a counterexample, which either is possible. But it's not known. What is the best strategy of the second player in round 2 and in 3 and higher is not known. And solving this conjecture is like one of my favorite open problems. So if you have some time, if you are interested, this is a very simple, this is a, concrete puzzle to think about. So this is a situation for the all-round game in dimension 1. So already in dimension 1, we can see that the situation can get quite complicated if you play the game for many rounds. But really, Voronoi games and these facility location problems are most meaningful in 2 dimensions. That's how you think of, houses and everything. So what happens in 2 dimensions? So again, let us go back to the case where I have a bunch of points in 2 dimensions and I want to play the game for 1 round. So endpoints are there now in the plane, and I want to place, player 1 will place a facility followed by player 2. Okay? How do I do that? So in the 1 round game, P1 will place F1 followed by P2 will place S1. So I think that in the case of the 1 dimensions, the strategy of the second player here isn't that hard. So suppose the first player placed at F1, right? What is the best strategy of the second player? Well, if a first player is at F1 and the second player is at S1, then the number of users served by F1 and S1 is determined by their perpendicular bisector, right? It's determined by that Voronoi diagram. Whatever is on the one side of the perpendicular will be F1, the other side of the perpendicular, it will be S1, right? So how do I find F1? So I take a line through F1 and I rotate this line so that the number of points on one of the sides is minimized. So I rotate the line through F1 so that the number of points on one of the sides is minimized. And then I place F1 just a little above the line, very close to that point, F1. Then the perpendicular will be just parallel to this dotted line. This solid line is a perpendicular. And because it has the least number of points on one side, that is the best strategy of S1. Right? Any questions? So if that is the best strategy of the second player, what is now the best strategy of the first player? So second player will do that if the first player places at F1. What would the first player do? How would the first player choose the point so that it does not give much away of its users to the second player? So what is the strategy of the first player? Any guesses? How would you do it? There's no answer. You have to think about how to do it. What would be a process to find that point? So remember,
to look at the other side of the line.
Yes.
And see if both the parts have same number of points on it.
Can you repeat that?
Look into two regions created by that line, the partition, and check whether both the parts have same number of points on it. Same number of points on it.
Not necessarily same, right? So you have this line through F1, which has the least number of points on one side. That is called the supporting line of F1. I have to find the point F1 which has the maximum number of points on one side of its supporting line. The maximum would not be necessarily half and half. Such a point might not exist. But I need to find the best possible supporting line, basically.
Can we slide on the initial line where the F1 is placed to in the slide to the bit left on the same line so that we can.
So if you slide it upwards, then by this cut it may be half and half, but by some other cut it can be less than half. And then on one of the sides it will be more, so S1 will get more. So this is, you are fixing a slope. If you fix a slope and then move, then of course you can get half and half. but there might be a different cut with a different slope on which side there might be more points. And if there's more point on any line, any slope, then S1 can take off that slope by placing very close to that, like drawing parallel line to that. S1 will take all of it, right? So you have to find the best supporting line such that a point such that the line which has the least number of points on one of the sides is maximized. Does that make sense? So the point F1 where this is attained has a name in statistics. It's a well-known object. It is called the half-space median or the cookie median. It is not necessarily half and half, but it is some point such that the minimum number of points that is there on the supporting line is maximized. So it's a classic object in statistics, it's a classic object in algorithms, and you can compute it in almost linear time, in log cubed n time. So this is the optimal strategy of player one. But this is only one round game. What about multi-round games? So for multi-round games, even for 2 rounds, almost nothing is known. Almost nothing non-trivial is known. This is a wide open area. So what are bounds on worst possible payoffs? What are some optimal strategies for computing these things? None of that is known to any degree of satisfaction. Most of the results known in this part of the world are kind of like, on these problems are nothing is really known. So it's a wide open area again, and lots of interesting things to think about. Okay, so in the remaining time I will talk a little bit about the rabies project and how these ideas became relevant in designing rabies vaccination campaign in Arequipa in Peru. So let me talk a little bit about the group at Penn which works on these projects. So the Zoonotic Research Center at UPenn works on designing rabies vaccination campaigns in the city of Arequipa in Peru. So rabies, surprisingly to me when I started this work, and maybe to most of you, is that it's still a major problem. It causes about 59,000 deaths every year. 40% of them are children under the age of 15. The Pan American Health Organization recommends that there is an annual vaccination coverage. So dogs are vaccinated to up to 80%. If that number is attained for over a period of time, then they believe that rabies will be eliminated. But this number has not been attained in Arequipa over the last 8 years. Now, Arequipa has a structure which is in some sense similar to the structure we have here in India. So there are lots of free-roaming dogs in the streets, but these dogs also have a home where they come at night to stay. So, these free-roaming dogs can potentially spread the rabies, but they do have a home, so it's upon the homeowner to go and vaccinate their dogs. So how would you go about doing this campaign? The most natural thing would be, well, I have to place some vaccination sites somewhere in the city, so I do some facility location. I place some K vaccination sites based on minimizing some objective function. I can do K median, I can do K center or something. So we will discuss the results in just a moment, but once you start to do this in a real data, on a real actual application, you realize there are lots of things that can go wrong, lots of practical issues. So you run the algorithm, and algorithm says you place a facility here, and then you go and tell this to the Department of Health, and they say, no, that we can't place it there because that location is inaccessible. That location cannot be used, or things like that. One very important practical issue that emerged during this study was what data we had. We had the location of the houses, and we had the location of the possible places where you could place these vaccination tents. We needed to calculate the distance from the house to the nearest vaccination tent. This distance, from the data we had, we could compute the Euclidean distance. But the Euclidean distance is of no use. We need to compute the walking distance, because no one will go from one place to the other like that, like a bird. No one will go there. No one will fly. So we need to find the walking distance. How do you do that? That wasn't so easy. So we had to use Google Earth, pay Google some money to get some data from Google and extract that data from Google Earth. to get at the actual data in hand of the walking distance. An example of what a practical situation often looks like. So here is the solution. Here is what came out of the experiment. So there are 3 plots here. The left-hand side is the solution of the mass dog vaccination campaign that was done 10 years ago. There are 20 sites which are placed. Each site is marked with a triangle, and its catchment area, the area it serves, is colored with some color. This was done by the Ministry of Health in 2016. This did not use any algorithms. This was just some human guess. They looked at the map and placed it somewhere, and they got something. This is the p-center optimization. This is the p-median optimization. So let us look at how these 3 things compare. So these 2 optimizations are optimizing some function of distance, sum or maximum. So you would expect that if you place it by optimal strategies, then the distance that people have to walk will be significantly less. And indeed, that's what's happening. So here in the second row here, I have the distance histogram. So for each user, I compute its distance to the nearest facility. There are several hundreds of such distances. I draw the histogram. The histogram in the second and the third column here are more peaked than this, which means that more people have to walk less, which is what it should be. Okay? Moreover, if you compare between the histogram of the p-center and the p-median, you notice that the p-median has a few points which are quite far away in the tail, a few points where you have to walk a lot. The p-center, on the other hand, is much more, the peak is to the left a little bit more. And again, this is believable because p-center will minimize the maximum. So it will tend to make a lot of distances close to the maximum. P-median, on the other hand, will minimize the sum. So 1 or 2 distances can be large, but the overall sum will be small. Different objectives. Another thing that we looked at, and this is something that was not optimized, but it was important from a practical point of view, was each vaccination site serves a number of houses. You don't want to put too much load on one vaccination site, because if there is a long line of dogs waiting in some camp, then there is going to be a disaster. So we looked at the histogram of the catchment area, which is the number of houses in each vaccination site. And we note that for the p-median, the catchment is most balanced. And we want the balanced catchment so that this kind of load is equally distributed. So this is interesting, like, the solution and how it behaves. So the k-median distance distribution has a higher peak and a longer tail than the k-center, and the k-median catchment distribution is more balanced. So several problems emerged from this study. What ideally we would want to do would be to minimize something that optimizes both the walking distance and the catchment sizes. So that's kind of a geometry problem which one can formulate out of this. What we ended up doing in the paper was something that was neither the k-median nor the k-center, but something that is somewhere in between. So because each of them has its benefits and have different types of objectives that they maximize, one way to combine them is the following. So for each user, what you do is you look at the distance to its closest facility. Instead of minimizing the sum of all of them or just the maximum, you look at the sum of the R maximum. So look at the sum of the maximum, the second maximum, and the third maximum, let's say, and then minimize that. So if you take R equal to n, you get k-median. If you take R equal to 1, you get k-center. Taking a value in between is somewhat of an interpolation between these two objectives. So this is what we ended up doing in the paper is something related to that. And this gives you more spatial evenness. So in the paper, of course, we did not use exactly this objective, but we used a statistical model, which doesn't involve directly distance, but some logistic regression model that involves distance. And then we minimized a kind of top R maximization algorithm. I'm not going into the details, but that's what was done. But what it leads to is new geometric and algorithmic questions. In particular, this new problem that comes out of it, of minimizing the top R distances, when you look at something in between K median and K center, has very interesting geometric structure, very interesting algorithmic properties. Okay, so this is an example of a problem that emerged by actually looking at a real application, real data, and formulating a new theory question that fits into this classical framework and gives you new results. Okay, so I'm going to stop here and see if you have any questions. Thank you.
Thank you, Bhaswar, for your wonderful talk. So we'll open up for questions now. Any of you have questions, please feel free to ask. Maybe I had a question like, I mean, can you go back to the slide of that two-dimensional problem also? Yeah.
That one?
Yeah. So I think you explained, probably I missed it. So how do you I can see two lines. So I forgot the significance of the dotted one.
No, so the dotted line is, so the dotted line is the most important one. So you want to find a line through F1 which has the least number of points on one side. So you take a line through F1, you rotate it, and you stop where in a place where one of the sides has the least number of points. So that line is the dotted line. Now, if one side has least number of points, then the other side has the most number of points. So S1 will try to get that side. So this upper side is what S1 will try to get. So S1 will place essentially on the other side very close to F1, so that the perpendicular bisector between F1 and S1 is this solid line. So it will give a little epsilon, you move it upward so that you get essentially the entire upside. Does it make sense?
Yeah. Thanks.
Yes.
Okay, if there are no more questions, then we'll end this talk over here. Thank you again.
Thank you. Thank you very much.